All right, here we go. Hi, everyone. Thank you so much for joining the community meeting this morning. I'm just going to run through our normal housekeeping updates before we jump into the technical presentations. A reminder of our mission and what we're trying to build: state-of-the-art ML compiler ecosystem built collaboratively with our hardware and software partners, many of whom are here with us today. And leveraging the best of XLA and MLIR. And so we always start off these meetings giving people the opportunity to introduce themselves in case someone is new to the meeting. So please feel free to speak up if you'd like to introduce yourself to the group here. Any new folks?
Hi, I'm Bartek and I'm from Intel. Actually, I'm from the same group as Moshe.
Hi, Maciej. I'm a colleague of Bartek and colleague of Moshe, so Intel Habana.
Awesome. Thank you so much for joining us today.
Thanks.
Anyone else? All right.
I'm also new to this meeting. In fact, I'll be presenting, which is why I'm here. So I'm Reed. I'm from Google on the XLA GPU team.
Welcome, Reed, and thank you for signing up to present. Let's see. Okay. So just moving on. This is an overview of how we collaborate in the SIG. Just for anybody who is new and is looking to figure out how to follow development updates, community conversations, and good stuff like that. We host a monthly meeting on Zoom every third Tuesday at 8 a.m. Pacific time, which is now no longer Pacific Standard Time, or now is Pacific Standard Time. So apologies for the non-US folks who had to deal with that. One caveat is that we are looking at moving the December meeting up by a week, so it does not fall so close to Christmas, and we'll go over that at the very end of the meeting. We have a rotating meeting host and scribe usually, and we try as much as possible to propose and share our agenda and have discussions in the community repository ahead of time. And then after this meeting, we'll be obviously we're recording this meeting. We'll share notes, slides, and the meeting recording the day after. These meetings usually include development updates, an overview of design proposals, and any community topics going on. And here are some handy links out to our different code repositories, discussion channels, and of course, our Discord and community meetings. So again, you can access all of these links either from the community repo and OpenXLA, which is just /community, or from these slides when we publish them later. So moving on, we have two development updates today. First off, we're going to hear from Reed, who is presenting the RFC for FP8 support in XLA and stable HLO. And after that, Mehdi from the OpenXLA team at Google will be giving us an update on the refactor effort that's part of us pulling XLA out of TensorFlow and into the OpenXLA GitHub organization. So I'll hand it to you, Reed.
All right, thank you. I will be presenting FP8 in XLA and stable HLO. So next slide, please. So I'll give a background just on what FP8 is. So FP8 refers to any 8-bit floating point format. And traditionally in machine learning, people have mostly used FP16, BF16, and FP32 floating point formats. An advantage of using the two 16-bit formats is that many accelerators run operations faster in them. And so recently, NVIDIA released their new generation of GPUs called Hopper GPUs. And these support an even lower precision format called FP8. And NVIDIA claims that they could run machine learning models end-to-end 1.2x to 1.5x times faster compared to 16-bit formats. And so in particular, Hopper GPUs support two different FP8 types that differ in the number of exponent and mantissa bits. And I'll get into the details of these D types on the next slide. And so we want to support these D types in XLA and stable HLO so it could take advantage of the performance increases on Hopper through FP8. And so we have an FP8 RFC. And so please take a look if you're interested. And I'd really like to emphasize that the RFC is not yet finalized. So if you have any feedback, please let us know, because we still can and are willing to change design aspects if people disagree with them or if we don't like them. And I'll also emphasize that the RFC is proposing adding the FP8 types supported in NVIDIA Hopper. And NVIDIA, Intel, and ARM have agreed to use these particular FP8 types. But other vendors are also supporting their own forms of FP8. And these differ in usually very minor details, like how do you encode NAND, and whether inf is supported and whether -0 is supported. And so for now, we are just proposing to add the NVIDIA, Intel, and ARM FP8 types, which there are two of. But if other vendors want to add their own FP8 type in the future, they could create their own proposal, and we will consider taking it into stable HLO and XLA. And so I will present the FP8 design that the RFC proposes. And the RFC also discusses how the design might evolve in the future to use these special quantized types and ops that exist in stable HLO. But unfortunately, these types are not yet ready to be used with FP8 in XLA. And so they're not part of the initial design. In this presentation, I will only present the initial design, but please take a look at the RFC if you're curious how the design might evolve. And I'll add that the RFC does not make a recommendation on whether we actually should use these stable HLO quantized types in the future. It just discusses them as a potential thing that we can do, because it's important to understand the context of why we're not using them. Next slide, please. So these are the two D types that Hopper GPUs support. And you could see from the diagram here that E4M3, as the name implies, has 4 exponent bits, 3 mantissa bits. E5M2 has 5 exponent bits and 2 mantissa bits. And so there's a trade-off here between the dynamic range and the precision of the format. And so E4M3, according to NVIDIA, should typically be used on the forward pass, and E5M2 should be used on the backwards pass, because that results in the optimal model quality. But also note how low the dynamic range here is for E4M3. The max value is only 448. The min value is only 2 to the -9. Next slide, please. So it is quite unfortunate how low the dynamic range is here. And in practice, if you just try to use E4M3 in your model, and even E5M2 to an extent, your model quality will not be the same as using the 16-bit formats. And so to prevent this underflow and overflow, every tensor needs to have a scalar number called a scale associated with it. And if you're familiar with integer quantization, this is essentially the same thing. It is a form of quantization here, in particular symmetric quantization. And so this is best described with an example, which I have on the slide. So you can see on the left that we have this FP32 tensor with 4 elements. And you can see the top left element there is very small, and it will underflow in E4M3. And so in this example, we have this scale, which is 2 to the -6. And to go from the FP32 tensor to the scaled FP8 tensor, you divide by the scale. So then you get the tensor on the right. And you'll see that when we scale, the tensor actually becomes within the representable range. So we have the smallest value being 2 to the -8, which is above the smallest value of 2 to the -9. And the maximum value of this tensor is actually the max E4M3 representable number, which is 448. So everything is good here. And it's no coincidence that our maximum value here, 448, is the E4M3 maximum value. In general, we want our scale to cause the tensor to barely not overflow. And the reason is that as long as you don't overflow, there's no issues. Like, you don't pay a cost for barely not overflowing. You only pay the cost when you actually do overflow. And so to prevent underflow as much as we can, we try to create our scale such that our tensor does barely not overflow, because that causes the values to be as large as possible without overflowing, and that prevents underflow to the maximum possible extent. Next slide. So unfortunately, unlike typical inference integer quantization, we cannot compute the scales ahead of time and then just use a single scale throughout all of training. We have to compute it dynamically. And the reason is that the weights change over time, and this affects what the best value of the scale is. And so we need to change our scales during training. And also, unfortunately, we can't just compute an optimal scale for each tensor every step and then use it on the same step, just because based on like the hardware, this just won't be fast. And so instead, the trick we use is that every step, we compute the scale for the next step, and then we use the scale computed in the previous step. So for example, in the diagram below, for step 1, you can see that we actually use the scale from step 0, and then we compute the scale for step 2. And this is just a very basic form of pipelining here that allows us to get the benefit of the dynamic scale while not paying a large performance cost. Next slide, please. So that's it for the background information on FP8. And next, I'll describe the changes we're actually going to make to support FP8. And so in our IRs, stable HLO, MHLO, and HLO, the only change we're going to make is we're going to add the 2 FP8 D types as supported by Hopper. And we're going to support passing tensors of these D types to various ops. And that's it. But it raises the question of how do we actually represent scaling here? And so one thing we could have done was we actually could have added like a scale parameter to pretty much every single op in stable HLO. But this would have been an incredibly intrusive and complicated change, and we did not want to have to significantly modify our op set just to support FP8. Next slide. And so this slide shows how we do support scaling. And the answer here is that we just use multiply and divide ops, which is simple. They already exist and they work for our purpose. But even with multiply divide ops, we have different ways that we could actually like represent running a specific op with scaled FP8 inputs and outputs. And in particular, there's 2 specific ways that we're proposing how frameworks should do this and init HLO to do this. And we're first going to show the generic approach in this presentation, and we'll next show the second approach. And so the generic approach is called the generic approach because it works for any single op. With this approach, you could run any HLO op you want with scaled FP8 inputs and outputs. And so the key idea to understanding both these approaches is that you never want to have an unscaled FP8 tensor, because as soon as if you have a scaled FP8 tensor and you try to unscale it, well, you're immediately going to overflow or underflow. The whole point of the scale was to prevent that. And so with this approach, we prevent this by always converting to FP16 first. So this example shows, we show both basically this Python pseudocode representing our HLO, and we have 6 steps written in English that also show the same thing. And so the basic way we represent this is that we have, we first in HLO, we cast our inputs to FP16 using a convert op, and then we unscale them. And this is called dequantization. And it's the exact same thing you typically do with integer dequantization. And then on step 3, we run the op with FP16 inputs and outputs. In this example, it's dot. Step 4 is computing the maximum of the output. And the only reason you have to do this is to compute the scale for the next step. That's just the formula for computing. It always uses the max of the output. Step 5 and 6 is the opposite of step 1 and 2. We just scale the output and cast back to FP8. And this is called quantization, which is the same steps you do for integer quantization. And so I may be thinking that this might be really slow because in step 3 here, we are running our op on FP16 inputs and outputs. So why bother with FP8 at all? Why not just run everything in FP16? And the answer is that your compiler could actually optimize this to it can emit code which actually will do math in FP16 and get the performance benefits of FP16. Or sorry, we'll do the math in FP8 and get the performance benefits of FP8. This is only how we represent it in HLO and stable HLO and MHLO, and it's not it does not necessarily match what code the compiler will actually emit. Next slide, please. So in particular for XLA GPU, we will use pattern matching to rewrite these 6 steps here into a single cuBOS call. And cuBOS, if you don't know, is it's an NVIDIA API for doing basic linear algebra operations like matmulls on a GPU. And so cuBOS presents an API that takes in the FP8 inputs and the scales for the inputs and outputs. And then it gives us the FP8 scaled output of the matmul, as well as the max of the matmul. And so with this, cuBOS itself will get good performance with FP8 compared to FP16. It'll fuse all of this into a hand-fused kernel. And so we'll get good performance here. And similarly for convolution, NVIDIA has another library that will do the convolution and also do these 6 steps automatically for us. And for things that aren't convolutions or dots, XLA will just fuse these itself without any sort of pattern matching. And in this case, we'll still get a huge memory bandwidth benefit from FP8 because only the inputs and outputs of your fusion are written or are read from or written to memory. And FP8 is half the size as FP16, and so we could read twice as many values in a given amount of time. So we could get large performance benefits from FP8, even though we represent all the actual arithmetic ops with FP16 inputs and outputs. Next slide, please. So this is the final slide. After this, there'll be a Q&A section. And so here we show just the alternative way to represent scaling in stable HLO, MHLO, and HLO. And so the left example on the slide is just the original example. It just without the comments indicating what steps every line belongs to. And on the right-hand side, we have our alternative example. And I see there's questions in the chat.
One question was, I can read it for you and for the recording. The question was whether we can upscale to something higher than F16, or is F16 a requirement here?
No, you could upscale to whatever you want. In general, like the pattern matching code is going to have to be aware of like what types it could upscale to, right? Because it's going to be trying to pattern match these with specific D types. But the fusion pass is generic, so we don't actually have to like hard code any particular high precision type. And for the fusion pass, I imagine that will allow the higher type to be FP16 or BF16 or FP32. Is that it? I think that's it. Please correct me if I'm wrong, but go to the previous slide. Yeah, so back to this. So the alternative way to scale is very similar. Only the first 2 lines in these 2 examples differ here. And so you'll see that at the start, we actually don't dequantize our inputs to FP16. We directly run a dot passing in the scaled FP8 outputs. And we have a dot whose output type differs from the input type. The output type is FP16, the input type is FP8. And so now our output is effectively scaled because we pass scaled inputs. And so on the second line of this function, we just unscale it. So in a sense, we're switching from unscaling the inputs to unscaling the outputs. And the big advantage of this alternative representation is that it directly matches what the hardware supports. On Hopper GPUs, the hardware that supports FP8 is in the form of an instruction which does a matmul with FP8 inputs and an FP16 output. And I imagine other FP8 hardware will have similar support. And this is also how integer quantization supports integer quantization, I guess. This is generally how hardware supports integer quantization. It typically has some hardware unit that takes int8 inputs does a matmul, and the output is either int16 or int32. So this will make it easier to emit code on backends, because instead of having to do this pattern matching, you just see you have a dot with FP8 inputs and FP16 outputs, and you just directly emit code for that. No pattern matching needed. On GPUs, this doesn't help us yet because we just delegate to cuBLAS or cuDNN, and this has such a high level API that we're going to have to pattern match in either case. But if we ever choose to emit our own matmul code instead of using cuBLAS, this alternative representation makes that a lot easier. But the disadvantage is that this only works for certain ops like dot and convolve. In general, it's not safe to just scale the output instead of scaling the input. Like if you have a sign op, say, you can't just, if you multiply your input by a certain amount and pass it a sign, that's not equivalent to instead doing the sign on the scaled input and multiplying the output by the same value. So no matter what, you're going to have to use the generic approach for certain ops. And so frameworks, if they choose to use the alternative approach, they're going to have to select between both approaches depending on what the op is. So there's advantages and disadvantages to both approaches, and I'm not really sure what's better at this point. There's been debate on the RFC over it. So for now, XLA GPU is going to pattern match both approaches. But in the future, if frameworks converge on choosing to just use just one approach for dots and convolves, we might only pattern match that particular approach. And we'll see what people think. And please comment on the RFC if you have an opinion here, or just comment in the Q&A section. Yeah, and that's pretty much it. The next slide is the Q&A slide. So any questions? Yeah, if not, then I think we can move on to Mehdi. And please comment on the RFC if you have any feedback or you just want to learn more about FP8.
I had a question. So is there any work ongoing in supporting FP8 data types in the frameworks like TensorFlow and JAX?
Yeah, there will be support in TensorFlow and JAX, hopefully by the end of this year. There's not going to be support for making it super easy to scale. We're not going to have some like very nice, say Keras API that does all the scaling for you. The user is still going to have to do some work by hand, a lot of work by hand, but it'll certainly be possible to use.
So one question about the design decision here. So you're making unscaling and scaling explicit everywhere in the IR, right?
Yes.
So the question is, isn't that kind of increases the size of your internal IR? Could you have maybe chosen an implicit encoding of that?
Yeah, so we didn't want to have to add like the scale, concept to a ton of ops. So yeah, it does increase the size of the IR. Like as I briefly mentioned at the very start, stable HLO has these special quantized types and ops. And these, like the quantized type actually represents both a tensor and a scale associated with it. And so in this case, you don't need to have all this scaling logic in the IR itself. It will be implicit through the use of the quantized types. But these are just not ready to be used in XLA yet. So we don't have a choice. If we want FP8 by the end of the year, we can't use them.
So in the future, you might consider that, and then you might have two ways of doing the same thing if you introduce quantize and dequantize type of thing?
Yeah, we might in the end choose to only fully support using the quantized ops if we go in that direction. And RFC has a lot of details on this. Okay, even if we can't force the user to not pass. Like the user can always choose to pass the original approach with divide and multiply ops. We can't force them not to do that because we will have the FP8 types, and they will be supported in ops. But we could choose not to pattern match those, and highly recommend that frameworks output the quantized types and ops in the future.
All right, thanks.
A question about the example. In this example, the dot product was a dot product vector with the vector itself, right?
Yeah, or a matrix, right?
I mean,
Yeah,
with
the
the
dot
same
off
vector.
could do like. Go ahead. Do you
Uh,
want to go
with-
back a slide also? Yeah, go ahead.
This is a dot product of a vector with the same vector, right?
Yeah, so in this example, to simplify it, I chose to do matmul with the same input, just because it makes the example shorter.
Okay, so just a small comment. This produces a very large positive value that usually won't fit your output data type because this is a sum of squares, right?
So it's not actually a dot product. The dot instruction will do like a vector. It can do a dot product, but it could also do a matmul. And you're right, a matmul is just a batched version of a sum of squares, right? A batched dot product.
Yeah.
Yeah. So in this example, you might have kind of a large value, but it's fine because we're using FP16. I mean, even FP16 has a pretty low dynamic range. It's the same as E5M2, but you could also choose to use BF16 or FP32, in which case it's very hard to overflow.
Okay, good. Thanks.
Reid, question regarding the quantized types. They're defined, but they're not plumbed through all the ops, correct? In the MHLO.
So they are, I believe, plumbed through all the ops on like the stable HLO level, and I think also the MHLO level, but XLA GPU doesn't know what to do with them. And not only that, on the ML, like they use the MLIR's quantized scalar types, and those don't support dynamic scales. So, I think these would be quite useful, but we just don't, we can't use them. It's like we have to make an MLIR change first, which just takes time. That itself will have to be an RFC.
Thanks. So in terms of the front-end APIs in JAX and TensorFlow, seems like we're going to go with pretty much the example that you showed, to the extent the user defines, uses those types and does the casting, we're going to pattern match. Is there going to be a way for the user to be aware that maybe the pattern matching didn't go through and the operation is actually not being done in FP8 and it's just being construed as is? Is that a valid question?
Yeah, it's a very valid question. Yeah, that's a good question. And the answer is unfortunately currently no. We don't have such a way. The RFC actually has kind of an example of this. It's called something like, I don't have the RFC up, I think it's called like major unresolved issue. We might try to add this concept of optional FP8 or kind of try to move more of the logic to compiler in the future, but the RFC makes no concrete suggestion on how this could be done. It's a really hard problem. For now, it's kind of like the user's just going to have to know what the compiler is capable of doing or have an educated guess of it.
Sounds good. Thank you for the great work.
Yeah, I mean, this is something that I would really like to resolve in the future because right now the user level API in JAX and TensorFlow is going to be difficult for users. We do want to make this better, but our initial goal is just to get the basic FP8 support in XLA so that TensorFlow and JAX could also have basic FP8 support. And the RFC does not propose going beyond that at this point.
I mean, sounds like this type of sanity checking will be easier in the second, like an alternative pattern, alternative API that you presented on the right side.
Yeah, I mean, the alternative only works for dot and conv and a few other ops.
Exactly.
But it's like, once you write it like that, it's kind of guaranteed that, yeah, because the GPU and other hardware will have direct instructions to do this. It's like, it's probably not going to upcast. I mean, every op will support FP8 arithmetic, and then the compiler will, in most cases, just silently upcast things for you because the hardware doesn't support like addition in FP8. So even with the alternative, it's not like a guarantee that, it will do what the user wants it to do.
Yep.
Yeah, any more questions? Oh, I see there's comments here.
So in the interest of time, I will recommend that it seems like most of the comments were resolved in chat. So we can add the Q&A both from, the live Q&A and chat, I think to the RFC itself, just so it's kind of clear what ongoing discussion has been had, if that's okay.
Yeah, that sounds good. And I'll respond to the chat.
Awesome. Thanks, Reed. And want to just, in the interest of time, move on to our next presentation, which is Mehdi giving an update on the TensorFlow XLA Refactor.
Hi, so I'm Mehdi. I'm in charge of launching this OpenXLA independent project from TensorFlow. And so we've been working very hard on refactoring XLA. So I presented the plan a few months ago. So as a recap, I'm just going to go over the high level first. Next slide. So the way we're going to untangle, or we have been untangling XLA from TensorFlow, is with a 3 repository solution. So on the left side, you have the pre-existing situation where it was pre-tangled. And so the way we cut the dependencies is by introducing a new repository that we call TSL, Tensor Support Libraries. And that contains all the support code that TensorFlow and XLA needs. Some of it is also used by JAX. So it contains service for the provider. That's only the code to start a provider session and record events, those kind of things. Also, all the cross-platform support libraries, the thing that allows us to open files on Windows or Linux and have a unified API, manage a thread pool, those kind of things. We also, the XLA runtime is using some pieces that were developed in TFRT called async value. So a very small piece of TFRT. So we've been extracting it from TFRT and moving it to TSL as well. And that way, TSL has everything that's needed by XLA on TensorFlow and can be a shared dependency of those 2 repos. At the same time, we've been moving stream executor inside XLA and reshuffling also some pieces of the TensorFlow runtime, some APIs and TPUs, all of this to make it so that XLA doesn't have any dependency on TensorFlow. Next slide. I think I have some text explaining this. Yeah. So you're going to see in the slides when we share them. This new repo, TSL, contains platform independent code. TensorFlow will depend on XLA and TSL. During this launch, we're going to vendor code. That means the code for XLA and TSL will end up in the end in TensorFlow third party. That's not going to be cross repository dependencies. That's just to simplify tooling and updates and testing in general for us. But fundamentally, the code will exist, will be developed in the XLA repo starting in February. So we were planning to deliver this in October. We are a bit late on delivering this new repo. So the current expectation is 1 month from now, mid-December, we should have all of it up and running. So next slide. So current status is that this TSL, the support library repository, is 99% complete. You can already clone the repo. You can build and test most of it. I linked to the CI script here. So we have a CI running on this GitHub repo. And yeah, we just have a few pieces. So if you look at the script, we are disabling some components that cannot build yet. But we are very close to this being fully complete. And we are now working on to getting XLA, which is currently located in TensorFlow/compiler/XLA, building and testing itself without any TensorFlow dependencies. And so that's if you look at the Git history on this directory, you can see that we've been doing many refactoring and updates to cut those dependencies and cleaning this all up. As part of this work, we've also figured that the current directory layout in XLA is a bit confusing. For example, the service directory has 238 header and public component exposed, which is huge. It's a huge flat structure. We are also developing the new MLIR flow for the XLA compiler in there. And so we've just published expected new directory structure for XLA that I think I pushed last night in the README for XLA. And I hope that my commit landed. So it's not going to be there. Yeah, it's there. So we try to document the directory structure and what we aim to achieve. Next slide. All right, next step and what to expect for the transition. Let me check if there are questions. Question about tests. Yes, we need to think about the testing and the CI. There's a question about how do we want to test XLA, in particular, what kind of, so first, I think we should amp up our unit testing, be more strict about having good coverage on unit tests. I think full coverage testing should be done on unit tests, but we also should have a stronger test suite inside XLA, because right now XLA really depends on its users to provide test suites, which is easy inside Google because we have a single monorepo in which we have all of our internal customers and we can run all of their code. So we should build a better test suite for XLA. I think a good starting point may be JAX, because JAX has a very thin layer on top of XLA, and so JAX test suites can be a good way to bootstrap what we need. But this is still open in terms of how we want to structure and organize all of this. So yes, we've also been staffing up more on infrastructure on our side, and so some people are ramping up and will own developing CI and testing in 2023 for this new OpenXLA repo. In the meantime, what we're going to rely on is we're going to continue to rely on the existing testing, and the slides that I'm going to present now may also clarify a little bit. So something that will stay is that the Google internal repo is a place of synchronization, meaning the flow that we will have next month is that we're going to publish this new repository. We're not going to accept pull requests at first because we won't have the CI in place, and we won't have the tooling to manage all of that. So we're going to continue with the existing flow, which is you can already contribute to XLA through the TensorFlow repository. So if you're a contributor, you can open a pull request to the TensorFlow repo. And the way we merge pull requests is that we actually merge them in our internal code base, and immediately we always continuously mirror our internal code base to GitHub. And so what's going to happen next month is that we're also going to mirror the internal code base to the OpenXLA XLA repository. And so you're going to have the same code externally that will exist in two places, the TensorFlow repo and the OpenXLA repo. It's always going to be perfectly in sync because pull requests are merged in the internal repo, and our automation will push the same commit at the same time in both repositories. And that's going to probably last until January because we don't expect to make big changes over the break. Next slide. Now in January, what we plan to change is that we're going to open a pull request to the OpenXLA repo with some basic CI. And so you will be able to start contributing directly to the XLA repository, and we're going to merge those pull requests the same way as we merge pull requests from TensorFlow repo. Now, until February, we're going to accept pull requests in those two repositories to ease with the transition, because people probably already have pull requests in flight, code that they intend to contribute in TensorFlow, and we want to not break everyone's workflow abruptly. So we're going to be able to merge those pull requests, and again, we're going to benefit from the fact that everything internally is in the same repository. We can get a pull request sent to the OpenXLA repo, or a pull request from TensorFlow and convert them into the same commit internally, and it always translates to the same commit externally as well. So that's gonna ease the transition. And then next slide, I think post February, we are gonna stop accepting pull requests for XLA in the TensorFlow repo, right? So you're gonna still be able to contribute to TensorFlow itself, of course. And the only way to be able to contribute code to XLA itself will be by contributing to this new OpenXLA XLA repository. And we're going to continue to land those pull requests in our internal code base and immediately mirror them to the XLA repository for now. And next, but I think it's probably my last slide. Yes, it was my last slide. So let's opening it up to question now, if you have any. I see a question about the XLA runtime, which I can answer. It's not really related to what I talked, but there's a question on the chat, which is how does the XLA runtime differ from the ERI runtime? And then you plan to share code between them. So the XLA runtime, we had a sorry, we had a technical presentation about the XLA runtime last month or the month before. So I invite you to visit those slides and the recording. It's not similar to the ERI runtime. It's at a very different level of granularity. That said, we are actively talking with ERI about convergence and how we want to handle that. I expect that next month you're going to have a very much clearer plan about how ERI and XLA will be intermixed and work together. But we are very interested in actively collaborating with the ERI team right now. Another question. I understand the OpenXLA repo is set up to have a CMake build system. Could you please confirm? Yes and no. The new MLIR implementation that we have for XLA is already building and testing with CMake. We haven't made plans right now to extend the CMake build to the entirety of the XLA repo. That said, we are open to do it. We may not have the bandwidth to do everything ourselves. So we would welcome patches if some people want to take this on. Otherwise, we would have to put it on a roadmap, but it's not going to be a high priority, I think, for us to extend the CMake build to all of XLA. So we may do it step by step and start extending it to pieces that we need. For example, we will want soon to test the end-to-end MLIR pipeline with PGRT. So we may add this. We are likely going to add some CMake component to PGRT so that we can have an end-to-end build doing this. But I'm not sure if the entirety of the HLO and service, what is today service directory, will be supporting CMake soon. All right, any other question? All right, if we don't have any other question, we can move on with community updates from Thea.
One more just thought of it. Is pull request open for TSL at the moment?
Oh, yeah, TSL is not on my slides. That's a good question. I think no. You can contribute to TSL through the TensorFlow repo. So TSL is in the same situation as XLA. Right now, you can send pull request to TSL inside the TensorFlow repo, TensorFlow/TSL.
Okay. Yeah, sounds good. Yeah. Okay. Yeah. We'll just kind of watch when eventually that'll kind of change, right? Along with XLA, you eventually.
Yeah, same plan as XLA.
Okay.
The thing is just like a matter of CI workflow. We need to keep track of things, get notification ready. What we don't want is to open up something to pull request and then they get, they don't get reviewed, they get forgotten.
Right.
And that's a writing experience for everyone. And so our focus right now is XLA. So that's why really this launch of having XLA in its own repo and having a good process for pull requests is really what we want to achieve. Of course, TSL will be open to pull requests. I just we haven't dedicated enough resources to set up the flow for TSL, and so right now the TensorFlow contribution workflow is the way forward. All right, Thea, if you want to take over for community update.
Yep, thanks, Mehdi. And so Mehdi, where's the best place to ask follow-up questions on the refactor progress right now, in case people have questions or people who watch the recording later do?
Maybe what we should do is start a thread on GitHub discussions for the refactoring, linking to the slides and saying like, hey, we presented the slides at the meeting today. If you missed it and you have questions, let's discuss in this thread.
Okay, sounds good. That sounds like a plan. All right, so just a couple of outgoing community updates. We're going to start, for some reason, something's missing. We're going to start looking at listing out the active RFCs that are going on in the community each month as well, just to make sure that no one's missed the opportunity to give feedback. Right now we have 3 different stable HLO RFCs aside from the FP8 one that Reid presented today. Compatibility and versioning, bounded dynamism, and evolution, which is essentially just how we plan on evolving stable HLO and some initial thoughts about what the kind of RFC process would look like. So we're still firming up, what our overall process is for reviewing proposals. I'm going to publish something in the community repo, just standardizing. Here's where you can find out about the proposals that are active. Here's how long we plan to leave them open for comment. And I think as we dive into governance, which should have some updates for everybody in December and then also in January, we can figure out like how do we go forward with decision making on different proposals and RFCs. That being said, we also welcome the community working with the OpenXLA community to create RFCs that are not from Google. So please, reach out in the discussions. If you have an idea that you'd like to flesh out, Discord as well works, or obviously in the other channels that you have available. We'd love to see more conversation coming from all the partners here as well. And then I think the one last parting note is that I've rescheduled the December community meeting to the 13th. So that, before it was landing on the 20th, and I assume many people will be taking that week off for the holidays. So hopefully as many people as possible can join. We're also really eager to have presentations from the community present at these meetings, but also I think there's the opportunity to create like ad hoc tech talks that are off cycle from the community meetings. If you have something to share or present, would love to work with you to set up a meeting specifically for that, to showcase, your project or some updates that you want to share, and reach out to me directly or start a discussion thread on the community repo, letting us know, and we'll be happy to set that up. Yes, I think that is all we have today. Are there any questions, kind of more general questions out of the band of the topics we discussed today, or ideas for topics that you'd like covered in upcoming community meetings that we haven't addressed yet? All right. Okay, sounds good. Well, as usual, we will publish this slide to YouTube and also add it to the meeting archive directory on the community repo, and also create some discussion topics in GitHub around the refactor, and add some of the Q&A that's happened to that RFC, just so that's more legible. And we'll try to get a bit of a head start on publishing the agenda for December 13th, since it's coming up more quickly than in just a month. So please, again, let us know if you have any agenda items you'd like to add, even if it's just a informal discussion. Those are totally fine. It doesn't need to be a really formal presentation. And we look forward to seeing you then, and in GitHub and Discord in the meantime. Thanks, everybody. And thanks, Reed and Mehdi, for presenting.
Thanks, so, bye.
Mhm.
Thanks. Yeah, bye.
Thank you. Bye.